Okay, so welcome to the class today, guys. We're talking about linear inequalities and absolute value. We're going to sort of extend some of the ideas that we talked about last time in section 2.7, but now to the setting of inequalities. And we're also going to be solving what are called linear inequalities. There's just like solving linear equations, except for one detail. When you multiply or divide by a negative number, you have to do something slightly different. But otherwise, everything is essentially the same that you would have done for a linear inequality. And then we'll talk, the hardest questions sort of in this section 2.7 here are those ones that include absolute values. But really, it's just a matter of rewriting them into what are called compound inequalities. Okay, so what are our learning objectives for today? Today we've got 4. And the first one is the most important of our learning objectives, okay? And this first one is to use interval notation. I'm going to spend quite a bit of time here talking about interval notation, even though there's not really any specific question in Infinity that goes over interval notation. And it's just because this is the most important topic or the most important objective in this section of the textbook. And that's because you'll use interval notation fairly often in your future math courses or courses that depend on this algebra course, okay? So this stuff will come up again. In the context of today's lesson, we're going to first derive some properties of inequalities. So we'll talk about those properties and inequalities, and then we'll use those properties to solve inequalities in one variable algebraically. And the method is going to be essentially what we're used to, just isolating the variable on one side of the inequality. And then, like I said, the final thing is we'll talk about how to turn an absolute value inequality into what's called a compound inequality, and then write out the answer in terms of interval notation. But again, the most important objective from today is that you understand and you have some experience with interval notation because it will come up. It can be difficult for students who've never seen interval notation before because you use some of the same notation you would use for an ordered pair. But you have to sort of think about what the context is, and that tells you if you're using an interval or if you're using an ordered pair. Okay, so there's not really a whole lot of content today, but there are a lot of examples. We're again going to start with interval notation. And anytime that you're imagining an interval, you really should sort of think about a number line. And so you should have a picture like this in your mind. Here we've got the number line starting at 0, and it's going off to infinity as it goes to the right. It also goes to the left as well. There's negative numbers there. But what we're highlighting in this picture graphically are the numbers that are bigger than or equal to 4. So for example, 5, 6, 6.5, 7, 9.1, 10.111, all these numbers here as we go to the right. And this arrow here means that we continue on forever, going to the right. Oh no. Okay, so it looks like a couple of people might be having issues with the audio or the video. Is it the video or the audio that you guys are having trouble with? Okay, so here I'm moving the audio. Let me reconnect one more time because I'm using my phone for the audio. Maybe that will give us a better experience with, although Beatrice is telling us that it sounds good to her. So let me just take a survey. If it's good for you guys, give me a thumbs up. If you're still struggling, we'll reconnect. So if you can hear me, give me the thumbs up. Otherwise, we'll try to reconnect one more time. Okay, Angelique, Isha, Melissa is breaking up. Logan looks good. Eric looks good. Jordan's a little bit off. Okay, so because there are so many students that are giving me a thumbs up here, I think I'm going to continue on without updating. I would suggest that those students that might have some trouble leave the room and re-enter the room. And if you continue to have the same issue, I would say I'm going to record this session, so it should be up. So you should be able to watch any of the parts that you might have missed this afternoon, okay? Make sure, though, that if you do that, that you're taking notes and posting your notes. Okay, so just keep me updated, guys. I'll post the recordings. If you miss something, just keep up to date on the recordings. All right, and again, keep me updated in the chat, right? It's really important that we have good quality here, otherwise it's difficult for everybody to follow along. But anyway, we were talking about the interval from 4 to infinity, right? All the numbers to the right of 4 on the number line, and we highlighted it here. And we would write this in an equation or an inequality. I guess it's not an equation. Equations have an equality sign. It's an inequality in the following way. We would say these are all of the numbers x, which are bigger than or equal to 4. Okay? So these are all numbers which are bigger than or equal to 4. And we could write it in another way as well. We could put the 4 on the left-hand side here, and we would switch this inequality around, and we could write it this way. So this is saying 4 is less than or equal to x. In other words, this is just another way of saying the x's that are bigger than or equal to 4. And here I'm putting an equal sign underneath because there's this dot right here at the 4, right? It's a closed dot, so it's telling us that we should include it. Now, there's sort of a nicer way to write this out in terms of notation, and that's what we call interval notation. And here what we'll do is we'll use a bracket, and then we'll write the 4. And that bracket indicates that we're including the 4, that there's a closed circle there at the 4. And then we just go on forever to infinity, right? And I'm just going to put an infinity here and then a closed, a parenthesis there. And what this means is that we just go on forever, right? So this is everything from 4 and less than infinity. And everything is less than infinity, so that includes everything in that yellow box, okay? So we could have also had an open circle here, so we could have said not including 4, and in that case we would put a parenthesis there. So there are lots of different sort of options here for interval notation on the endpoints. Let me now go to a slide that sort of explains all of the different options, and this might be a little bit overwhelming, but it has all the various options, and we'll focus on several of them. Because even though there's a lot of different options here, several of them are really similar to one another, okay? So the first ones that you really want to focus on are the ones that have just an A and a B. So this is called the open interval because both have parentheses from A to B. This one down here is called the closed interval from A to B, and that's because both of them have brackets. You're including the A and the B. And then there are the half open ones. So one is a parenthesis, one's a bracket, then this one's a bracket and a parenthesis. So these 4 are really, really similar to one another, right? And in terms of a number line, what you have here is the numbers from A to B. So let me jump so you can see the board real quickly. So here we have a number line, and we have the numbers from A to B, and what we're looking at is basically everything in between. And on the endpoints, you can either have an open circle or a closed circle, right? You can have an open circle or a closed circle. The open circle means that you exclude the endpoint, and the closed circle means you include it. And in terms of the notation, that's the difference between the bracket and the parentheses. So this up here, 2 parentheses, just means that you do not include A and B, but it's everything in between A and B. Down here, if you include 2 brackets, then it's everything between A and B, including both A and B, right? And then these guys here, if the bracket's next to the A, you include the A, but you exclude the B if it's a parenthesis. So that's including the A, but excluding the B, and then vice versa, right? So the parenthesis here tells you to exclude it, and the bracket tells you to include it. So these 4 are the most important ones, but these are the ones where there's no infinity symbol at all, okay? So the other symbols that you're seeing here, the other intervals, all have infinity symbols. So here's an infinity, here's a negative infinity, infinity, negative infinity, again, infinity, oh, that one's negative infinity, infinity, and then this last one down here, negative infinity all the way to infinity. This one down here usually is not used that often, but it means all real numbers, so it goes from negative infinity to infinity. But what I want to point out with all of these infinities here that I'm highlighting is that you never use a bracket, okay? So that's just a reflection of the fact that negative infinity and infinity aren't considered real numbers, and so you can't include them in your interval, okay? They're always going to be excluded. So anytime you have a negative infinity or an infinity, then there's a parenthesis, okay? So that's what I'm highlighting here. And then what you do with the other piece of the interval is you just put a number there. So this is the set of numbers from A all the way to infinity, excluding A. And then you also have the numbers from A to infinity, including A, okay? And then same thing for the right-hand side. So this is from negative infinity all the way up to B, including B. And this is from negative infinity all the way up to B, excluding B. So the bracket means include B, the parenthesis means exclude it. And then the last one and the most difficult piece here is this last one down here, because it has this union piece. And in this case, it's probably best to draw a picture of what's going on so you can sort of understand. And there are sort of more options here, but these are the ones that when we have parentheses. So again, we have this number line, we have A, we have B here. And here I'm going to put open circles. They could be open or closed, but I'm going to put open circles. And instead of putting the numbers between A and B, I'm going to put the numbers that are larger than B and the numbers that are smaller than A. Okay? So this interval we would normally write as negative infinity all the way to A, excluding A, so we'd put a parenthesis. And this interval over here we would write as B to infinity, excluding infinity and excluding B. But it's going to be often the case when we're looking at compound inequalities that we want to put these together. Okay, that we want to include both this interval and this interval together, and we do that with a big union symbol, which is written as a U. Okay, so this region that's smaller than the A but bigger than the B is this region from here to here. And you could have included either parentheses or brackets. Okay, in this picture or this diagram that I had in the previous slide, it only does the parenthesis version, but you could have brackets there as well. Okay, and that will come up when we're talking about absolute values, so those compound inequalities. Okay, so lots of different stuff here. And again, don't get this confused with the ordered pair AB. This is the set of numbers between A and B, even though the notation is the same. You have to think about context. Okay, so let's do just a couple of examples so everybody's on the same page here with this sort of stuff. And I'm going to put some pictures up on the board of intervals. And as I do them, I'll ask you guys to put the answers in the chat, okay? So the first one that we'll look at is, so here's 0, 1, 2, -1, -2. And in this case, we'll have a closed circle at 2 and an open circle at -3. And we're looking at the numbers in between the two of them. Okay, so think about what your answer would be. Don't put it in the chat yet. I'm going to ask you to sort of answer them in a certain order here. Number 2, let's look at now sort of a similar number line here. So here's 0, here's 1, here's 2, here's 3 in this direction, and then -1, -2. In this case, we'll have a closed interval, or sorry, a closed circle at -1 and a closed circle at 3, and we're going to the right here and to the left here of -1, right? So going out in those two directions. And then the third one that we'll talk about is one where we have an open interval. So now we're going to go from 0 to 2. So here's 0, 1, and 2. I'll put -1 there and 3 there just so we can see the rest of it. There's an open circle at 0. There's an open circle at 2. And we're interested in the numbers in between them. Okay, so the easiest of all of these guys, let me put that so you can see the whole screen here. The easiest of these guys is number 3, right? So let's go ahead and start off with number 3. And again, that's starting with the open circle here at 0 and an open circle at 2. What do we have for that interval? How would we write that in interval notation? As soon as you have it posted in the chat box. This is -1, this is 0, 2, and there's 3. Okay, so we use parentheses in this case because they're open circles. We started at 0, we ended at 2. So yeah, it just looks like the ordered pair 0, 2, but indeed in this case it means all the numbers between 0 and 2. Notice this is a whole infinite collection of numbers. It's all the numbers between 0 and 2. Okay, what about the one on the top? Notice here we have an open circle on the left and a closed circle on the right. What's the difference here? How are we going to take that into account? Notice the numbers change as well, right? So it's not going to be 0 and 2. Okay, so we're starting off here at -3. We put a parenthesis because it's open. We don't include that, and it goes all the way to 2. We include the 2. Okay, so there's that one. And then this one here is going to be a union. So go ahead and add in the union one for us. We've done that one. Yeah, so both of these ones are closed. And just as a hint here, there's going to be a union in this one. So what do we have for that union? Okay, good. So this one's closed, right? So this is closed from 3 all the way out to infinity. And then over here, this one goes from -infinity. We always put a parenthesis there because infinity and -infinity aren't numbers. And then it goes all the way up to -1, and you include the -1. Okay, and that's the answer for this one. So anytime you're seeing an interval, you should always think about what it looks like in the number line, right? Or vice versa. They should be sort of interchangeable for you, thinking about them back and forth. Okay, so let's come back to our slides, and let's change gears now and talk about solving inequalities, linear inequalities. And the reason why we were talking about interval notation at all is that the solution set for an inequality is typically going to be an entire interval. It's not going to just be a single number or a pair of numbers like it was for the quadratic equation. It's going to be an entire interval, and that's a reflection of the fact that there are infinitely many different solutions for most inequalities. Okay, so we need a few properties, and I want to sort of point out why these properties are true. The first one is that you can take an inequality like A is less than B, right? So you can take an inequality like A is less than B, and you can add whatever you would like to both sides of the inequality, right? So if you add C to the side with A, then you can add C to the side with B, and you get an inequality that still is true. And the reason why is if you think about a number line, the picture that we have here is that A is to the left of B, and if you give me some C, for example, like say C is this far, between here and here, if I add C to A, I get A plus C, right? It just moves it to the right. If C is positive, it just moves it to the right by C. And if I added C to B, it would do the same thing here, right? So this distance would be C, and right here would be B plus C. And so we still have A plus C is to the left of B plus C because adding C just moves everything to the right by C unit. And C could have been negative as well, right? If we would just subtract some number from both sides, it would have moved it to the left. So you can add or subtract something, and it's just a matter of sort of moving back and forth on the number line. And just so you can see everything I wrote there, all I said was this distance from here to here is C, and that distance from there to there is C. So you're just moving everything to the right by C or to the left by C. Okay, so that's the addition property. And the point is just that it's exactly the same property as you would have done if there was an equal sign here, right? So instead of inequality like that, it's what you would do with the equal sign. Nothing different. Okay, so if you multiply both sides of an inequality by a positive number, nothing changes either, right? So if you start off with A is less than B, you can multiply both sides by C, so you would get A times C on this side, and B times C on this side, and everything would be good, provided that the C is actually positive, right? Provided that the C is positive. And I can give you a quick proof of why that's the case, just so we can see how it's related to positive times a positive. So first, let's start off with A is less than B. So that's the if part of this statement. And we also have that C is greater than 0. Okay, so C is positive means that C is bigger than 0. So here we'll use the addition property that we had up here, and I'll subtract a from both sides. If I subtract a from this side, I get 0. And if I subtract a from this side, I get b minus a. So this means that b minus a is positive. And this one here means that c is positive. Okay? And if you take two positive numbers and you multiply them together, right? If I take two positive numbers and I multiply them together, I'm going to get a positive number. So in other words, if I take b minus a and I multiply that by c, that's a positive times a positive, the whole thing is still going to be bigger than 0. Okay, and I should have written it this way. Let me write it like this. So it's still bigger than 0. That way it looks like the formula we're using. Okay, so positive times a positive means that we're still bigger than 0, so positive. Now distribute the c to both of these terms. You get 0 is smaller than b times c minus a times c. So I'm just distributing the c, that's the distributive law. And then we'll use the addition property again to add ac to both sides. So if I add ac to both sides, I get ac here, ac plus 0 is ac. And on this side, I'm left with bc. And that's what we wanted to conclude, that a times c is still less than b times c. Okay, so the point of all of this, if you didn't follow what I was saying here, is just that this fact relies on the fact that a positive times a positive is still positive, okay? Now, what changes is if you multiply by a negative. And this is really the main thing that you need to be aware of when you're trying to solve an inequality, is that if you multiply both sides of an inequality by a negative number instead of a positive number, then what happens is the inequality has to flip. Okay, and what do I mean by flip? Well, here we've got a is less than b, and over here we've got the opposite sign, right? So this was the less than symbol, and this was the greater than symbol. So it flipped around from the left-hand side being smaller to the left-hand side being larger. Okay, let's see maybe why that's the case, just really quickly. And what's the difference here? So we still have a is less than b, and if I subtract b from both sides, I still have b minus a is positive. But the difference now is that we're assuming c is negative, right? And if I assume c is negative, that means that it's smaller than 0. That means that this guy is negative. And if I multiply a negative times a positive, I don't get something that's positive. In fact, I get something that's the exact opposite. I get something that's negative. So that's where the flip is coming in. And if I flip that side, I have to flip that side, and I flip that side as well. And that's where the flip comes from, right? The fact that you get a positive times, a negative times a positive becomes negative. So you have to take that into account every time that you're doing this. And so that's what this third piece of this multiplication property is telling us, okay? So now the last part of this just says that all of what I'm saying has nothing to do with using just this less than symbol. It works for the less than or equal to symbol. It works for the greater than symbol or the greater than or equal to. So you can use any one of those four and these three properties. You just have to be careful about when you multiply or divide by a c. And so the name of the game is going to be exactly the same. When we're trying to solve an inequality, we're going to try and isolate x on its own. So we'll add or subtract things, multiply and divide. And we just have to be careful about when we divide by a negative. That's the only difference, okay? That's the take-home message from these slides. If you didn't understand the proofs, please read through the book. The book has a pretty good explanation of this as well. So if you need a little more detail, you can hit that up there. Okay, so before I get into the examples like we see in Infinity, I want to talk about one last thing, how we deal with absolute values. Okay, and they're going to turn us into what are called compound inequalities, and this is why we needed to use that sort of union symbol when we were talking about intervals. Okay, so you're going to get an algebraic expression, right? So a whole entire expression here. This capital X could be something like x squared plus 3x plus 4, just a whole entire expression, and a positive number k. And if you have an inequality that has an absolute value in it, you'll want to put it in this form first. What do I mean by this? Well, you isolate the absolute value on one side of the inequality, right? So it looks like this. And once you isolate that absolute value on this side of the inequality, you convert it into a compound inequality. And what a compound inequality is something that has two inequalities in it. So we go from having one inequality to having two inequalities. And the payoff here, though, is that we no longer have an absolute value. So we go from something that had an absolute value to something that doesn't. Now, it's a little more difficult to deal with because now we have two inequalities that we have to deal with, but they're equivalent. Let's sort of think about why. So in this case, the absolute value of x, the only way that you're going to take a number and have the absolute value be less than k is if that number was actually less than k. If it was bigger than k, its absolute value would be bigger than k. But we also have to be careful that it's bigger than negative k, because if it was any smaller than negative k, its absolute value would be bigger than k. And we'll go through some examples of that. But here, you're just going to convert over to this. And when we're doing something like an absolute value of x is bigger than k, well, then you have to break it up into an or statement. Okay, again, this is another compound one. We'll do one example of this sort of at the end. But what this means is that the x had to be bigger than k, or the x had to be smaller than negative k. That would be the only two ways that you would get something whose absolute value is actually bigger than k. So we'll convert these absolute value ones into compound inequalities, and then write these solutions in terms of interval notation. Okay, so that sort of concludes all of the main content for today. Here again, you just have to be careful about multiplying by a negative or dividing by a negative. And then here, absolute values get converted into compound inequalities. So let's actually do some stuff that you might see in Edfinity, right? So what we're going to do now are just examples of the types of questions Edfinity will ask you about solving these inequalities. Okay, so this is question number 4 that we've looked at. And we're going to look at 13 minus 7x is bigger than, right, greater than 10x minus 4. And what we're after here is figuring out what values of x can I plug into this inequality that will result in something that's true. Like, let me give you a quick example. If I were to plug in 0 for x, this part would disappear and I'd get 13 on this side. And if I plugged in 0 on this side, this part would disappear and I'd get negative 4. And 13 is indeed bigger than negative 4. So x equals 0 is a solution to this inequality, but there's many other solutions as well, right? There are, in fact, infinitely many different solutions, and we'll need to write down the set of solutions in terms of an interval. Okay, but luckily, we have most of the tools already we need to do this. We just have to isolate the x on its own. So let me ask you guys, if you wanted to isolate the x on its own, what would be your first step? So in the chat, let me know what you would do. Okay, so Alan here is saying, let's subtract the 13. Jordan's saying we'd subtract the 7x. Well, we want to maybe add the 7x, right, if we wanted to get rid of it on one side. But I see what you're saying. Yeah. Let's go with the 13, right? Let's go with subtracting 13 because I want to make sure that there's a negative in front of an x, so we have to deal with a negative. Right? It might be easier if you see to move this over here so you don't have to deal with any negatives next to an x. But let's say we just wanted to subtract 13 from both sides. If I subtract 13 from this side, I get negative 7x. The inequality stays the same direction here because all I'm doing is adding or subtracting something. And then up here I would get 10x minus 4 and then minus 13. Okay, and I'm just explicitly writing it out. Normally you would just write the minus 4 minus 13, right? So here we get negative 7x is bigger than or equal to 10x. And then we've got this minus 4 minus 13, which is minus 17. Okay, so I was just following, somebody's advice. If you wanted to move the 7x over first, all we have to do is isolate something, right? So now if we're moving this 17 to this side, what should we do with the 10x? How do we get the 10x to the other side? Okay, so Alan here is saying subtract the 10x. Anybody else? Yeah, so it's just subtracting the 10x, right? We want to get this x over here on just one side of the inequality, so let's subtract 10x. So we'll get negative 7x, and we'll subtract 10x on this side. And then on the right-hand side, the 10x's just cancel out, so we'll get negative 17. But negative 7 minus 10, that's negative 17x is greater than negative 17. And so this is why I did it sort of in this funky way of subtracting the 13 first, because now we're confronted with having to deal with dividing by a negative, right? Because now it's tempting, and this is why a lot of your algebra teachers tell you don't just divide both sides by negative 17, because it's tempting to just put a bar on both sides and divide by negative 17. But if you did that, you'd be incorrect. Because in fact, what you have to do is you have to flip the inequality around. We're going to divide by negative 17. And when we divide by a negative number, we have to flip the inequality around. So this side divided by negative 17 is just going to give us x. And on the right-hand side, we'll get negative 17 divided by negative 17. So here, that tells us that x is less than or equal to 1. Okay? So we've rewritten this inequality. We've just isolated the x. This is the same set of steps that we would have done if there were equal signs here, but we're just sort of putting an inequality instead. And yeah, in Wilson, the difference is that if you divide by a negative, you've got to flip it around, right? You've got to flip it around. If we were dividing by a positive number, we wouldn't have to do that. But when it's negative, we do. And notice that what this says is if I pick any number that's less than or equal to 1 and plug it in here, I should get something that's true. For example, if you plug in 0, like I said before, when you plug in 0, you get something that's true. And if you plug in anything that was less than 1. Now, on a number line, what does that look like? So here's 0, here's 1, here's 2, 3, here's negative 1. Well, we include 1, and it's anything less than, smaller than that 1, right? So on a number line, it looks like this. What does that give us in terms of an interval? Right? How do we write this as an interval? We've included the 1, that's a closed circle. Yeah, Destiny, you only flip if you divide by a negative or you multiply by a negative. And that's a reflection, if you remember the proof that we were talking about, of the fact that a positive times a negative is negative. That's where that rationale comes from. That's where the reasoning comes from, of why we do it. Yeah, if it was just dividing by 17 instead of negative 17, we wouldn't have to flip the inequality. Okay, but let's come back and chime in with, so yeah, Alan's got it here. Dalton's got it. All right. So we're going all the way from negative infinity. We put a parenthesis because we could never include it. And we stop at 1. We include the bracket there. And that would be the solution set to this inequality. And again, what we're saying here is that anything in this collection, you pick anything over here and plug it in, you get something that's true. Anything on the other side of this, you get something that's false. Right? So it's telling us exactly the solution set of the inequality. And there are infinitely many solutions in this case. That's why we have to use interval notation. Okay. So that's a good example. Let's now do one where we've got to deal with some fractions, right? So here we had to just sort of, not have to deal with any sort of denominators or anything like that. But in infinity, they get a little bit tricky with fractions. So let's talk about one where you'll need to use some fractions. In this case, we've got negative 5 over 6x is less than or equal to 3/4 plus 8 over 3 times x. Again, we're interested in what values of x can I plug into this and end up with something that's true. That's what the solution set is telling us, right? It's going to end up being an interval. Okay. So for me, the first step that I did is I didn't want to deal with any negatives next to my x, right? So this negative 5, 6, I don't want to have to multiply and move things around. So in this case, what I'll do is I'll just add 5, 6 to both sides of the equation. And that gets rid of the negative that's next to the x, right? So adding 5, 6x to both sides of the equation, we get zeros here, 3/4 plus 8 over 3x, that's just that one, and then just add the 5 over 6x. And you'll notice that now we just have positive numbers next to the x, okay? We have positive numbers next to the x. Now on the side here, let's do this, let's add them together, right? What's 8/3 plus 5, 6? Notice the common denominator here is 6, right? So somebody tell me what we end up with here when we add 8/3 to 5, 6. 21/6, and 21/6 gives us what in terms of reduced? Does it look like reduced? Seven over 2, yeah. Right, because 21 is 7 times 3, 6 is 3 times 2, the 3's cancel, you're left with 7 over 2. So we could have just jumped right to the following. 0 is less than or equal to 3/4 plus 7 over 2x, because that's what would have happened if we added those two together, right? And notice that this inequality is just saying whatever that is, it's positive, right? Whatever this is, it's positive. Okay, so subtract the 3/4 to the other side so that we isolate the x on its own. And you'll notice that I haven't changed the inequality. I'm keeping the same less than symbol because I haven't divided or multiplied by a negative. And now, because I put everything on that side and I made sure that these guys are all positive, now I can divide by the 7 over 2 and isolate the x on its own. So divide by 7 over 2. On this side, we'll get negative 3 over 4 divided by 7 over 2. And on the right-hand side, the 7 over 2's just cancel out. How did we get 21? Well, so here we have to multiply the top and bottom by the common denominator. So the common denominator here is 6. We have to multiply the top and bottom here by 2 in order to get a 6. And 2 times 8, that's 8 and 8, that's 16. 16 plus 5 is the 21. Okay, so we need a common denominator down there, huh? Here I just subtracted the 3/4 to cancel it out over here, so that's where we're getting the negative 3/4. Okay, and then let's do this division as well. So over here, I'm just putting this in a box because this is not something that you should do sort of in your supporting work. You should just sort of do it on the side or in your head. Negative 3/4 divided by 7/2 is the same thing as multiplying by the reciprocal, right? So that's multiplying by 2/7. So we get negative 6 over 4 times 7. So 4 times 7 is going to give us 28. So top by top, bottom by bottom. Or if you wanted to, you could have canceled that too. And so you get negative 3 over 14. So really, this is negative 3 over 14 is less than or equal to x. Okay? So again, all I'm doing is doing this division that I had here, multiplying by the reciprocal. Okay, does anybody have a question about this? I know that sort of the fractions are really kind of throw people off, but if anybody has a question, if you're good with it, just give me a thumbs up and we'll move on, because I'm going to erase these two guys here and actually now write out things in terms of interval notation. So if you've got it, let me know and we can erase it. Okay, thanks, guys. So, what does this inequality look like? Well, it looks like anything bigger than negative 3 over 14. Okay, so anything bigger than negative 3 over 14. So if we're looking at a number line, here's 0, here's negative 3 over 14. It's really close to 0 because negative 3 over 14, that's a really small decimal number, but it's to the left of 0. We include negative 3 over 14 because it's a less than or equal to, so there's a closed circle. And it's anything that's bigger than, right? So the x is bigger than that, so it's the stuff to the right. So it looks like this. And in interval notation, we would write that as a bracket, negative 3/14, and we go all the way out to infinity, and we put an open parenthesis there. And again, anything that you pick in this interval will be a solution to the original equation that we've had. Like, for example, 0 is in this interval. If I plug in 0, I get 0 on this side and 3/4 on that side. Bam, we've got an inequality that's true. So that interval that you're writing down is the set of solutions, and it's infinite, right? There are, anything you pick in there will make the inequality true. Okay, so that's it. That's like the story for the algebraic, like the linear inequalities. Now, we want to do a couple of examples of the absolute value, right? So how does the absolute value come into the mix and change things? And let me go ahead and talk about, before I talk about the absolute value, let's just do one more example. But it's an example of something you'll have to do along the way with an absolute value. It's what's called a compound inequality. Okay? So slightly different than what we were looking at before. In this case, I'm going to look at 2x plus 2. And we're going to say that, okay, it's less than 6. So this would be sort of what we were doing before. But now with a compound inequality, there are two inequalities. And this one has a strict one and then one with an equal sign. So this is less than or equal to. And it's, in this case, 3 is less than or equal to 2x plus 2. So this is a compound inequality. And these are the sorts of inequalities that you'll end up with anytime you deal with an absolute value. But here, we've already sort of just put it in compound form, so let's talk about it. Here, we'll want to isolate the x on its own. But we have sort of three different components here. We have the thing on the right, the thing in the center, and the thing on the left for the inequality. And we'll just do everything to each piece of this, right? So we don't need to separate it into two pieces. We can work with it all at once. If I want to isolate this x on its own, what should I first do? Should I add something, subtract something, multiply, or divide? How do I get that x on its own in the center? Okay, Alan's saying -2. Angelique's saying subtract the 2. Yeah, we want to get the 2x on its own, so we want to get rid of this 2. But if we do it to the center, we've got to do it to the right and to the left. Okay, so here we get 3 minus 2. 2x plus 2 minus 2, the 2's are going to cancel, so I'll just cancel it out there. There's just a 2x on its own. And then here we would do 6 minus 2. And if you can see it, you could write it down like this. 3 minus 2 is just 1. And 6 minus 2 is just 4. So if you could have seen it, you could have jumped right to 2x is in between 1 and 4. Okay, so now if I want to isolate that x on its own, what do I need to do? Add, multiply, subtract, divide. What should I do? Okay, divide by 2, right? We subtracted 2, now we've got to divide by 2. And it's nice that it's a positive number because we don't have to mess with the inequalities. If it was negative, we'd have to flip things around. But here we're going to divide by 2. And if I divide by 2, I just isolate the x on its own. We don't have to change our order of our inequalities, so those stay the same. And what we do on the right-hand side, we've got to do on the left-hand side as well. So we divided by 2 here, so we'll divide the right-hand side by 2 and the left-hand side by 2. Okay, so 4 divided by 2 is just 2, so this is really saying that x is in between 1/2 and 2, where we include 1/2, but we exclude 2. So on a number line, here's 0, 1, 2, 3. So we go all the way to 2, and we exclude 2, so there's an open circle there. And then there's a closed circle at 1/2. 1/2 is right in between 0 and 1. It's the halfway point, so there'd be a closed circle there, and it's the stuff in between. So this would be 1/2 to 2, include the 1/2, exclude the 2. And that's the solution set to this inequality. And again, it's a compound inequality because there's two pieces here. So when you're dealing with a compound inequality, whatever you do to the middle to isolate the x, you do to the right and the left. And I think Alan was alluding to in the book, they also mentioned the fact that you could have just separated this into 2. Like you could have thought about it like this piece here on its own, and then this piece here on its own. That's fine to do it that way as well, but I sort of prefer this method. So this is how you'll see me doing it. But, you know, just so you realize that the book does offer that as a method, and if that's the way you see it, then, you know, by all means do it, right? As long as you're getting the right answer and you have the right supporting work, you should be good to go. Okay, so in the last 5 minutes here, let's talk a little bit about absolute values and how you'll deal with those. And I'll just jump back and remind you of what you have to do. So you'll isolate the absolute value on its own on one side of the equation, and then depending on which of these you have, less than k or greater than k, you'll rewrite it either as a compound inequality like this, or two different compound inequalities together. Okay, so let's actually see an example of that, and we'll write out the answer. So in this case, let's look at the absolute value of x minus 1 is less than or equal to 3. And we only have about 4 minutes, so I'm going to go through this a little bit quicker than maybe I should, but we'll go through it really quickly. So here, the only way the absolute value of x is going to be less than 3 is if x minus 1 is less than or equal to 3 or bigger than or equal to negative 3. Because, for example, if it was something like negative 5, if it was smaller than negative 3, if it was negative 5, the absolute value of negative 5 would be 5, and that would be not true here. 5 is not smaller than 3. So here, the first thing we do is rewrite it as a compound inequality, and then we want to isolate the x on its own, so we just add 1. So we get negative 3 plus 1 is less than or equal to x, which is less than or equal to 3 plus 1. Now, minus 3 plus 1, that's negative 2. Here we have the x isolated on its own, and then over there we've got 4. And we include both the 4 and the negative 2. So in interval notation, there's negative 2 to 4, including both negative 2 and 4. And I'll show you the whole board there so you can see the whole answer. Okay, so the one extra step that we had here was just, man, right here, right? How do we rewrite it as a compound inequality? Now, this one was nice because you've already isolated the absolute value, but there are some where the absolute value is not isolated. So let me do one last example and we'll be done with everything. So why is it negative 3? It's just following this this procedure here, right? Because if it was any smaller than negative 3, the absolute value would be bigger than 3. Okay, and then just so, I'll stick around for like 5 minutes or so after class if you guys still have some questions, but we want to do one last one that'll help you with infinity, because sometimes you'll have to isolate the absolute value. So here's one, negative 2 times the absolute value of x minus 4 is less than or equal to negative 6. Okay, so here, it's not in that format because it's negative 2. So our first step is to isolate the absolute value, which is the absolute value of k minus 4, on its own. So we need to divide both sides by negative 2. So here we'll get negative 6 over negative 2. But notice what we did. We divided by a negative to isolate that guy. So we'll have to flip it around, okay? So this becomes, or it changes from being a less than symbol to being a greater than or equal to. So we divided by negative 2, so it becomes this. And now we can rewrite this as the absolute value of k minus 4 is bigger than or equal to 3. And this was the other type of inequality that we had in that compound setup. So this is one of the second type down here, right? So something is bigger than k. And what it means is that we can separate it into two pieces. That k minus 4 is either going to be less than or equal to negative 3, or k minus 4 is going to be bigger than or equal to 3. Right? That's the only way that we're going to get the absolute value of this thing to be bigger than 3. If we're actually bigger than 3, or if we're less than negative 3, something like negative 5. Okay? Okay, now we just isolate the k here. We add 4 to both sides. So we get k is less than or equal to negative 3 plus 4. Or on this one, we get k is greater than or equal to 3 plus 4. So here we've got k is less than or equal to 1. And here we've got k is bigger than or equal to 7. And that's an or statement. Okay? So when we look at the graph, here's say 0, 1, 2, 3, 4, 5, 6, and 7. What's going on here is k can be bigger than or equal to 7, so we'll include 7, and we can be bigger than or equal to it, so out in that direction. Or k could have been less than or equal to 1, so we include the 1 with a closed circle and go this direction. Okay, so yeah, sorry, Wilson, I didn't answer your question here, but let me just finish off the answer, and then if you have some questions, we'll come back and answer them after the recording. So now we just rewrite this in interval notation. This is negative infinity all the way up to 1. And then this one is 7 all the way out to infinity. We use parentheses there because that's infinity, and that's negative infinity and infinity. And then gluing them together, the or part is the union. So anything in this green region, in this interval, is going to be a solution to this inequality up here. Okay, and I'm just going to pause or stop the recording now. Thank you guys for being here. If you have some questions, I'm more than happy to stick around for the next 5 minutes or so and answer them.